Today, the world record for one of the field's oldest open problems is held by a rent-by-the-hour machine learning pipeline. The target is omega, the asymptotic exponent that defines the absolute minimum number of steps required to multiply two large matrices together. A new paper has just pushed the upper bound of that exponent down to 2.371177. The final run that secured this exact limit took roughly 5 hours on a single GPU. Historically, every decimal improvement to this number required painstaking, human-led mathematical proofs to shave off even a fraction of a digit. This time, Google DeepMind researchers teamed up with Josh Ullman, Virginia Vasilevska-Williams, and Renfei Zhou, the specific theorists whose own papers set the records being broken here. If you want to track how modern computation is breaking open classical math problems in real time, hit subscribe. We are watching progress on an asymptotic limit transition from a rare theoretical event into an infrastructural engineering loop, one that will execute again the moment the tooling improves. To understand how they did it, we have to look at what they omitted. They did not discover a new mathematical theorem. Instead, they extracted unexploited slack from an existing one. The current bounds rely on a modern refinement of the laser method, known as combination loss analysis. This framework was mathematically sound, but it was constrained by a massive central optimization problem, a problem too complex to solve at scale without automation. The theorists were trying to optimize a specific structure called the Coppersmith-Winograd tensor, specifically the version where the parameter q equals 5. Because of the computational shear wall, all previous manual work by human theorists stopped at a maximum recursion level of 3. The team's first move was to reformulate the combination loss problem, restructuring the math specifically so it could be processed in a much larger computational setting. The theorists realized their framework had provable room left to explore. They decided the fastest path to claiming that territory was raw compute power, rather than searching for a deeper proof. The immediate goal of this structural rewrite was to push the search exactly one step deeper, from recursion level 3 to recursion level 4. Stepping up a single recursion level dramatically alters the parameter space. At the level 3 baseline, the math operates with approximately 25,000 parameters. Moving to level 4 forces a 280-fold geometric expansion of that network. In an instant, the parameter count hits 7 million. This volume breaks traditional mathematical solvers. Extracting the exact minimum value by hand, or even with standard scripting, becomes impossible. Advancing the edge of theoretical mathematics has essentially become an extreme, high-dimensional machine learning problem. To conquer a space with 7 million parameters, the team built a transferable optimization recipe. The entire foundational environment is built in JAX, utilizing tensor parallelization stretched across up to 10 distinct axes. Inside this environment, they implemented softmax parameterization. This strictly forces the iterative steps of the solver to respect the required distributional constraints of the math. Next, they applied Sinkhorn-Knopp algorithms to process the heavy maximum entropy computations. They used implicit differentiation to maintain stability, ensuring backpropagation didn't collapse as it moved through the complex inner solver. Finally, they ran the standard atom optimizer on top of this stabilized architecture. This exact gradient descent stack offers a newly proven blueprint for any research team trying to solve optimize a certificate problems in the hard sciences. The stack itself required an orchestrator. They wrapped it in an outer loop driven by AlphaEvolve, Google's large language model-based code evolution system. AlphaEvolve evolves the optimization program's code from generation to generation, iteratively refining the algorithm itself. To accelerate the process, AlphaEvolve uses a warm start approach. It begins each new generation's algorithm precisely at the best solution point discovered by the previous version. There is a critical scientific vulnerability here. Machine learning relies on floating-point arithmetic. Floating-point math introduces tiny rounding errors, and in pure theoretical computer science, a rounding error invalidates the proof. To solve this, the pipeline executes a strict sanitization step. It takes the final floating-point solutions and strictly rounds them into precise rational numbers. As a failsafe, Any logarithm bounds within the equations are systematically rounded in the proper direction, ensuring absolute conservatism in the final claim. The results are then verified entirely with rational arithmetic. The final deliverable from this automated ML pipeline is a certified mathematical exactness, rather than a high probability prediction. We need to pivot to the unvarnished reality of what this paper actually delivers to the world. To measure the raw size of the mathematical win, we subtract the new bound, 2.371177, from the old one, 2.371339. That is an improvement of exactly 0.000162. This is strictly a battle over the fourth decimal place. To the software engineers and builders watching, your gem kernels, your QBLAS calls, and your GPU training throughput do not change by a single nanosecond. The laser method algorithms used to find these bounds are considered galactic. The matrix sizes required for this algorithm to actually compute faster than simple methods are astronomically beyond anything that can physically be modeled in our universe. While the theoretical race digs deeper into the decimals, practical, fast matrix multiplication remains firmly anchored to methods discovered in 1969. There is also an outstanding trust gap. As of writing, the authors are still preparing their verification repository, meaning the underlying code is not yet public. Consequently, the rational mathematical certificate has not yet been independently rederived or verified by a third party. The ultimate trust of this system will be a future attempt at recursion level 5. If the next exponentially larger jump in parameters only buys another fractional improvement of roughly 0.0002, the machine learning approach is officially asymptoting. The authors admit this themselves in the paper, stating that achieving larger, meaningful improvements to omega will likely require new mathematical ideas. This pipeline perfectly extracted every ounce of theoretical slack from a known framework, but pushing the actual frontier further will still require fundamental human intuition.